So moving on to Unit 2. So that's theme 2, which is limits, continuity, and derivatives. We start off with Unit 2.1, which is the tangent and velocity problems. So basically, theme 2, Unit 2.1 is introductory and illustrates the difference between average velocity over an interval and the instantaneous velocity at a point. Okay, so to start off, we're going to look at this example. So we're going to look at this function, y being equal to 2 to the power of x. So this is an exponential function. Okay, so our function is given by the green graph over here. So it's this one over here. So that's our y, and then we were going to plot a second line over here. So the blue one, this one, is going to be our second, and then we're going to have this other black line over here, and then our tangent, which is blue again. So they're correctly labeled over here. So the first question will be to find the equation of the second, PQ, which is from here to there. And in order to do that, we obviously need to first of all find the gradient of our second, and then we continue from there finding the equation of a straight line. Okay, so our gradient is given by the change in y over change in x, which is y2 minus y1 over x2 minus x1. And then we're going to have, so our q is 2, 4, and p is 1, 2. Therefore, we're going to just plug that into our equation. Then we get our gradient being equal to 2. After that, we're going to use the equation of a straight line to find out that our equation of the second is given by y is equal to 2x. Okay, so from looking on the graph, you'd actually see that moving this point q to q star and closer to our p value results in the second becoming a tangent to the curve at p. So at our point p, the more we bring our q closer and closer to p, our second becomes the tangent at the point p. Okay, so just define the major terms in Unit 2.1. Average rate of change, which is average velocity, is given by the gradient, which is just y2 minus y1 over x2 minus x1. And then you also need to know what is the instantaneous rate of change, which is usually represented by instantaneous velocity. So this is the limit as h goes to 0 of f a plus h minus fa everything over h. So that is what you need to remember from Unit 2.1, and that is all for Unit 2.1. Okay, moving on to Unit 2.2, which is limit of a function. So we'll start off with the basic definition of a limit. So it is represented by a limit of f of x as x goes to a is equal to L. And then our f of x, so our f of x over here can have values close to L by taking x sufficiently close to a, but please do remember that our x can never be equal to a. It goes close, very close to a, but then never exactly equal to a. Okay, so for example, we have f of x being equal to exponent of x minus 1 over x, and then we're going to look at f at point 1, and you have exponent of 1 minus 1 over 1. But what you should know is that f of 0 is not defined, since our 0 is not in the domain of f. So you cannot just plug in 0 into our function over there, because you're going to have an undefined function. Okay, so what we're going to do is plot this number line, and then we have our 0 over here. So we're going to analyze our function as we approach 0 from the positive and as we approach 0 from the negative. And as x goes to 0 from the positive, if you use your calculators to take it to do the steps gradually, you're going to see that as x goes to 0 from the positive, our f of x approaches 1. And as x approaches 0 from the negative, f of x goes towards 1 as well. Therefore, in conclusion, we can actually say that the limit as x goes to 0 of our function exponent of x minus 1 over x is equal to 1, even though f at 0 is non-existent. And there's an important limit that you're supposed to know. So limit as x goes to 0 of sine x over x, so that will be equal to 1. You should remember that one, because it's a basic fundamental limit. Okay, so the different ways to calculate the limit. So the first one will be direct substitution. So for example, if you're given limit as x approaches 2 of x squared minus 4 over x plus 2, you can directly substitute your 2 into the function, such that you have 2 squared minus 4, which is 0, and then 2 plus 2, which is 4, and 0 over 4 is equal to 0. So your limit will be equal to 0. Okay, so the other way of calculating limits is by factorization. So for example, if you check the same question as we did previously, if you look at your numerator, it's x squared minus 4, you can take that one as x plus 2, x minus 2, and then your denominator remains is x plus 2. Then you can simply factor out x plus 2 and x plus 2, such that you're only left with the limit as x approaches 2 of x minus 2. That will give you 0. So this is more applicable when your denominator is going to become 0. So for example, if this was x minus 2 on your denominator, then over here, if you do simple substitution, then you have 0 over 0, which is undefined. So you'd need to do factorization. Then x minus 2 and x minus 2 would cancel out, which means you'll be left with limit as x approaches 2 of x plus 2, which would give you an answer equal to 4. So just be careful on what you're supposed to use. Either use direct substitution, and if direct substitution doesn't work, then you can resort to factorization. So when you're doing direct substitution, beware of the denominator, because what you must know is that the denominator should not be equal to 0. And once you do substitution, then the denominator gives you 0, then you know you should go to factorization. Okay, next up we're looking at one-sided limits. So the basic understanding of one-sided limits is that when you look at a limit when approaching a limit from the negative and approaching a limit from the positive. So from the limit, it will be the one side, and from the negative, it will be the one side. From the positive, it will be the other side. Okay, so for example, for here, we have limit as x approaches a from the negative of f of x is equal to L, and your limit as x approaches a from the positive of f of x is equal to L. So if this is the case where you have both the limit from the negative and the limit from the positive giving you the same value, then you can clearly say that the limit as x approaches a of f of x is equal to that value L. Okay, but then if your two limits are not equal, so if the limit from the negative is not equal to the limit from the positive, then our limit of f of x as x approaches a does not exist. So please be wary of that. Okay, moving on. We can have an instance where we have limit is of 1 over x squared as x approaches 0. So that one, as you can see over here, is x approaches 0. It would be like, you can look at perhaps 0.05. 0.05 squared is a very small number, and so it's 1 over a very small number, which approaches infinity. So basically, the limit as x approaches 0 of a non-zero number and over a number getting smaller and smaller and smaller, then you're going to get infinity. So perhaps if you have 1 over, so any non-zero number, so maybe I'm just going to look at 1, and then over a number getting smaller and smaller, as you approach 0, so you can have x squared, x cubed, and all the other multiples of x. Okay, lastly, we're going to look at vertical asymptotes. Okay, so if line x is equals to a is a vertical asymptote, then one of the following is true. Okay, so the first part, the first condition that can be true is limit as x approaches a of f of x is equal to infinity, or limit as x approaches a of f of x is equal to negative infinity. Okay, the second condition that can be true is limit as x approaches a from the positive of f of x can be infinity or negative infinity. Then the last one will be limit as x approaches a from the negative of f of x is equal to infinity or negative infinity. So basically, when you get the limit of a function being equal to infinity, then you have a vertical asymptote. Okay, so for example, f of x is equal to 1 over x squared as a vertical asymptote at x equal to 0, since a limit as x approaches 0 of 1 over x squared is equal to infinity. So one thing you should know is how to locate the vertical asymptotes. Okay, so these are the steps that you're supposed to follow. So first of all, you find the domain. So make sure you find the domain of your function. Please make sure you do that. And if your a, if that point A is in the domain, then automatically your x is equal to a cannot be a vertical asymptote. But then if a is not in the domain, then now you can go back and test using our limits to see if x is equal to a is a vertical asymptote. So please make sure that you always use limits to test for vertical asymptotes. And that will be all on the theory of 2.2. Okay, up next we're going to be looking at the practice questions for theme 2.2. Okay, so the first one is find the limit as x goes to negative 1 of x squared plus x minus 2. So we say that the first thing that we're supposed to do is check by direct substitution. So we're going to have limit as x approaches negative 1 of x squared plus x minus 2. Then by direct substitution, you're just going to have negative 1 squared plus negative 1 minus 2, which is 1 plus negative 1 minus 2, which is just equal to negative 2. So first thing, you have to check the direct substitution. If that does not work, then you're going to use factorization. Okay, so moving on to the next one. Find the limit of x squared minus 4, x plus 2 as x approaches negative 2. Okay, so with this one, by direct substitution, if you put in negative 2 in our denominator, you're going to see that we're going to have a denominator of 0, and we said we cannot have a denominator of 0. So we're obviously going to use factorization. So its limit as x approaches negative 2 of x plus 2, x minus 2, everything over x plus 2, then that and that will cancel out, such that you have limit as x goes to negative 2 of x minus 2. Then if you plug in your negative 2, you're going to have negative 4 as your limit. So the next one is going to be limit as x approaches 1 from the positive of x minus 1. So for square roots, we know that we're not supposed to have a negative square root. So our minimum value that we can have in here is 0. Okay, so from the positive side, what you can do is just substitute. So it's basically limit as x approaches 1 from the positive of square root of x minus 1. Then if we just substitute 1 in there, then we're going to have okay, this is going to be 1 minus 1, just the square root of 0, which is equal to 0. So by direct substitution, you get your solution is 0. And then moving on, the next one is now from the negative. So from the negative side, you're still going to directly substitute in here. Then, because you have this one, and you can just substitute it there. And as it approaches 1 from the negative, then it's just going to get to 0 as well. Because you're just going to do the same thing, substitute your 1, then you're going to have 0, and the square root of 0, and then you get your final solution is 0. Okay, now let's look at limits as x approaches 1 of 1 over x minus 1, the denominator squared. Okay, so this is in the same group as 1 over x squared, 1 over x cubed, and so forth. As you can see that this one is a non-zero number, and then over here we have a number that is getting smaller and smaller and smaller. So because it's going to be 1 minus 1 giving us 0, so it's a number going towards 0, and 1 over a very small number is going to be infinity, as we've already discussed. Okay, so next we're going to look at limits as x approaches 1 from the positive of negative 4 over x minus 1. So it's basically the same as this one, just that this one now doesn't have the squared over here. But then the principle is still the same, so it's going to be limit so you can actually take out the negative sign outside. So negative limit of as x approaches 1 from the positive of 4 over x minus 1. And as this one gets towards 1, we're making this one smaller and smaller and smaller, and this one is a non-zero number. So we're going to put that negative first, it's negative, and then over here it's your infinity. So that's what you're going to get over there, negative infinity. Okay, so the other reason why we're saying it's positive infinity over here is because our numerator is positive, and then our denominator, since it's from the positive, so it'd be like 1.1, 1.2, 1.3, etc. Which means over here you're also going to have a positive number. So it's going to be a positive of a positive, giving you a positive infinity, and then you multiply by that negative. Okay, and then lastly, limit as x approaches negative 1 from the negative of negative 4 over x minus 1. Okay, so that's going to be given by, you can take out the negative limit as x approaches 1 from the negative of 4 over x minus 1. Okay, so over here we're approaching 1 from the negative, so we're going to be dealing with 0.9, 0.8, 0.7, etc., which means on the numerator you have positive, on the denominator you're going to have negative, and positive divided by negative will give you a negative. So you're going to have negative, the factor of negative infinity, and then negative and negative obviously cancel out such that you get infinity. So the limit is going to be equal to infinity. So please just be careful of the sign, whether it's negative infinity or positive infinity. Check your numerator and your denominator, and do not forget these ones that we're putting outside. Another case that you might be given is given f of x being equal to these. So it's 2x plus 1 if x is less than negative 2, x squared minus 1 if x is between negative 2 and 1, and 1 minus x if x is greater than 1. And then they say find the limit as x approaches negative 2 of f of x. So you'd actually see that at -2 we have two different scenarios. We have weights approaching -2 from the positive and weights approaching -2 from the negative. So you can have limit as x approaches -2 from the negative, which means we're going to be using this one. We're going to 2x plus 1. And that will be equal to, so just by direct substitution, -2 over there give you 2 by -2 plus 1. And then that will be equal to -4 plus 1, which is -3. And then limit as x approaches -2 from the positive, which will be this one. So it's x squared minus 1. And that will be equal to, by direct substitution, -2 squared minus 1, which is 4 minus 1, to give you 3. Hence, we can conclude that since our limit as x approaches -2 from the negative of f of x is not equal to limit as x approaches -2 from the positive of f of x, therefore limit as x approaches -2 of f of x does not exist. Okay, so now move on to the other one. Limit as x approaches 1 of f of x. So you see that there's x approaches 1 from the positive, this one, and x approaches 1 from the negative over here. So I split them again. Limit is x approaches 1 from the positive. We're going to use 1 minus x. Then by direct substitution, we're going to have 1 minus 1 giving us 0. And then limit as x approaches 1 from the negative. So we're going to use x squared minus 1, which is equal to 1 squared minus 1, which is just equal to 0. And since limit as x approaches 1 from the negative of f of x is equal to the limit as x approaches 1 from the positive of f of x, therefore our limit as x approaches 1 of f of x is equal to 0. Like that. So you just have to do everything step by step, especially when the function is divided into these parts. Okay, for the next set of questions, we're going to have determine the vertical asymptotes. The first one is f of x being equal to root of x minus 3, everything over x minus 9. So we say the first step, we look for the domain. So domain, from the denominator, we can see that x cannot be equal to 9, because when x is 9, then we're going to have a denominator of 0, which makes the function undefined. And then we look at the numerator. On the numerator, we have a square root, and with square roots, you can't have a negative x, so it's no negative square roots. So our x is greater or equal to 0. So basically, our domain is domain of f being an element of 0 to 9, and then 9 to infinity. That. Okay, so now we look at our denominator to determine our vertical asymptotes. Look at our denominator, and then the only number that is not in the domain from our denominator is 9. So we're going to look at x is equal to 9. So that's the limit as x approaches 9. So it can be either from the positive or from the negative. So from the positive of root x minus 3 over x minus 9. Okay, so first of all, we'll try by direct substitution, but then you'll see that that's 9 minus 9 giving us 0, which is undefined. So now we need to factorize. So with this one, we're going to say limit as x approaches 9 from the positive, and then the numerator remains as it is, and then the denominator now this can be root of x minus 3 over times root of x plus 3. It's still a two squares function. So over there, then we can see that that and that can cancel out, such that we'll have the limit as x approaches 9 from the positive of 1 over root of x plus 3. And then this value, if we substitute our 9, we are going to get square root of 9, which is 3, and then 3 plus 3, and that will give us 1 over 6, which is not infinity. Okay, we do that for the negative again. For as x approaches 9 from the negative, then you actually see that we'll still end up there, and we'll still get 1 over 6. Hence, basically the limit as x approaches 9 of f of x is just equal to 1 over 6, which is not infinity. So there is no horizontal asymptote. There's no vertical asymptote on our question f of x. Okay, the last question is f of x being equal to 1 minus x over x minus 5. So the domain of f is an element of all real numbers apart from 5. So we're looking at our denominator. The value that we can take is x is equal to 5, which is not in the domain, so we can test for it now. So the limit is x approaches 5 from the positive of 1 minus x over x minus 5. So by direct substitution, we're going to get 1 minus 5 from the positive over x minus 5, which is 1 over 0, which is undefined. So what we can do here, we can basically separate the functions. So we can have 1 minus x. Okay, let me just write as limit as x approaches 5 from the positive of 1 minus x times 1 over x minus 5. Then this, we can separate it as well. We can separate it further, so that it becomes limit as x approaches 5 positive of 1 minus x multiplied by the limit as x approaches 5 from the positive of 1 over x minus 5. Okay, so the first one, 1 minus x, that will just be negative 4 multiplied by, and then over here now we can see a non-zero number over a number that is getting smaller and smaller. And since we're using 5 from the positive, look at 5.1, 5.2, 5.125, etc. Which means our denominator is going to be positive and our numerator is positive as well. So that one becomes, then goes towards infinity. So we're going to be infinity, so it's negative 4 times infinity. So that negative sign is going to be incorporated into infinity. So then it's like 4 times a very large number is still going to be a very large number. It'll be negative infinity. So we say it from our conditions, if we can get negative infinity or infinity, then at that particular point we have our vertical asymptote. Therefore x is equal to 5 is a vertical asymptote. So that's it for theme 2.2.